Step into any cafe on a quiet morning. Phone lights up, emails flutter in, yet no wire touches the glass. An unseen something, call it a whisper in space, has reached across the room, carrying every word you will read. That whisper is an electromagnetic field. A gentle oscillation of electric and magnetic influence filling the air like an inaudible song. Not far away, an MRI scanner hums in a hospital basement. It persuades the tiny magnets inside human atoms to sing back detailed portraits of beating hearts and resting minds. Those images, too, are the handiwork of a field, radio waves coaxing nuclei to dance in precise rhythm. Now stretch your imagination a little further, to the detector halls beneath the Alps, where protons collide at nearly the speed of light. Out of the debris, physicists have glimpsed ripples in yet another field, a pervasive ocean called the Higgs. Unlike Wi-Fi, it cannot be switched off. It is everywhere, right now, pressing gently on every electron and quark, giving them the resistance to acceleration we experience as mass. If the electromagnetic field hands you emails, the Higgs field hands you weight. What, then, is a field? Picture the surface of a lake at dawn. Toss a pebble, and concentric waves spread outward. You do not create water itself. You disturb what is already there. In modern physics, every particle is just such a disturbance. A photon is a brief ripple of the electromagnetic lake. An electron, a more intricate swirl in its own dedicated pond. Even the warmth in your coffee is the combined jiggle of countless invisible waves. We were not always so wave-minded. For centuries, natural philosophers spoke of tiny billiard ball atoms bumping through emptiness. The shift from hard particles to soft fields is one of science's quiet revolutions. No banner moment, but a gradual realization that what we call objects are really packets of energy moving through continuous, layered media. Rocks feel solid because their waves lock together in tight patterns. Light feels intangible because its ripples glide through us with effortless grace. More astonishing still, the so-called vacuum, the space between stars, refuses to sit silent. Even stripped of matter and heat, it trembles with residual motion. Field lines flicker. Pairs of particles appear and vanish. A restlessness that underwrites lasers, superconductors, perhaps the birth of the cosmos itself. Over the next hour, we will tune our senses to these hidden symphonies. We'll see how field theory powers every text message, every fluorescent bulb, every GPS fix. We'll wander into the LHC's subatomic surf to meet the Higgs. We'll dive into graphene sheets, where electrons forget their mass and skate like light, and we'll ask a final daring question. Could space-time, the very arena of distance and duration, be one more field among many, rippling with our every step? Prepare to trade the comfort of objects for the elegance of waves. The universe is humming all around you. All you need to do is listen. Hold a compass flat upon your palm. The needle trembles, steadies, and points always to some far-off Arctic emptiness. No wind pushes it, no string pulls it. Instead, an unseen pattern threads the air, whispering directions to iron the way a conductor cues violins. We call that pattern a magnetic field. At every point in the room, there is a tiny arrow, too small to see, nudging anything with north-seeking courage. Slip the compass away and flick a wall switch. Filaments glow, street lamps ignite, whole cities pulse awake. Here another pattern takes charge in electric field, urging charges along copper veins. Lighting tungsten, brewing morning coffee, remove the wire and nothing flows. Reconnect, and the push resumes as faithful as tide and moon. These examples share a quiet truth. Space is not an empty stage where forces hurl objects like props. Space itself carries the instructions. A field is simply a map that tells everything, everywhere, how to move or turn. We do not glimpse the map directly. We infer it from what it makes matter do. The compass pointing, the lamp shining. Imagine, then, every square centimeter around you filled with overlapping lattice. Magnetic guides, electric prods, gravity's gentle downward pull. The world feels solid and separate, yet beneath it lies a mesh of influence, invisible but pervasive. Hidden geometry that shapes every gesture and glow. Now close your eyes and listen to a cello. Low notes stroke the room, high notes pirouette past your ears. Nothing solid crosses the gap between string and skin. Instead, the cello nudges the air itself, compressing and stretching it in rhythmic wrinkles we call sound waves. In one moment, the air molecules crowd together. A heartbeat later, they drift apart, peaks and valleys racing outward at the speed of a gentle breeze. To picture this, drop a pebble into a still pond. Rings ripple away, but the water molecules mostly bob in place. It is the pattern, the information of up, then down, that travels. Sound behaves the same, only the pond is invisible and three-dimensional, filling theater halls and forest clearings alike. Every wave owns two simple traits. Wavelength is the distance from crest to crest, the span between one push and the next. Amplitude is the height of the push, whisper, quiet, or thunder loud. No formulas are needed. Stretch the wavelength, and you hear a deeper pitch. Boost the amplitude, and the volume swells. These ripples in air remind us that fields are not exotic abstractions reserved for physicists. They are the most ordinary companions. Breath that carries speech. The bass that rattles windows. The crack of thunder announcing a summer storm. By starting with waves we can feel, we prepare to meet waves we cannot. Ripples of light, of matter, even of the fabric of space itself. Those lie ahead, waiting just beyond the next page of our cosmic field guide. Mid-Victorian Britain was a world of steam whistles and telegraph clicks. But in one quiet study at King's College, James Clerk Maxwell saw farther than rails and wires. On his desk lay two puzzles. Sparks leapt between charged objects, and magnets tugged iron filings into graceful loops. Most scientists treated these as separate tricks. Maxwell asked a bolder question. What if the electric push and the magnetic swirl are two faces of one deeper dance? Working with little more than ink, paper, and a mind-tuned to symmetry, he found the answer. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric one. Set either one in motion, and they chase each other through space, leapfrogging forever, a self-sustaining ripple. His equations predicted a speed 300,000 kilometers per second, and, when he checked, it matched the measured speed of light. Sunlight, candlelight, the glow of distant nebulae, all are electromagnetic waves. In that stroke, Maxwell united optics with electricity and magnetism, and offered humanity a new superpower, the ability to launch controlled ripples across empty air. Within a generation, Marconi would send Morse dots over the Atlantic. And a century later, Wi-Fi routers would beamcat videos through apartment walls. Yet every radio call and laser pulse, no matter how playful the content, still obeys the elegant choreography penned by Maxwell's hand. Fields, birthing fields. Light as the grandchild of an invisible marriage. Imagine dawn in a city apartment. A smart speaker requests the morning playlist. Halfway across the room, your phone obliges, though no cable links the two. The speaker's antenna shakes the electromagnetic field in rhythmic patterns, 2.4 billion ripples each second. Those ripples spread, weaken with distance like the glow of a flashlight, and arrive at the tiny receiver in your palm. The phone circuitry translates field wiggles into pulses of current, pulses into bits, bits into back, or Beyoncé. Step into the kitchen, pop a bowl of yesterday's pasta into the microwave oven, and another field trick unfolds. A magnetron inside the metal box squirts out waves just the right wavelength, about 12 centimeters to set water molecules spinning. Friction at the molecular scale becomes warmth at the plate. The oven cavity is sized so waves bounce back and forth, piling atop one another into standing crests, hot spots that cook food from within. You're harnessing Maxwell's waves in a corrugated metal cave. Even a simple coaxial cable, the fat cord feeding your router, acts as a waveguide, corralling electromagnetic ripples the way copper pipes steer tap water. Strip the cable's shield, and the signal fizzles, leaking strength into the air. Perhaps you've noticed that signal bars improve when you raise your phone near a window or shift your body. Your flesh, rich with salt water, absorbs microwaves and glass lets them sail through. In daily gestures, without equations or lab coats, we all negotiate with fields, seeking the clearest path for waves that whisper news. Laughter, alarms, and lullabies across the ordinary air we breathe. Fields, like rivers, can be steered. Peer inside a cut-open coaxial cable. A copper rod runs through a hollow shield, separated by plastic foam. When radio waves flow down this corridor, their electric part hugs the center, their magnetic part loops the walls. Perfect balance, none spilled. It is plumbing for light, coiling through walls to a rooftop dish. Scale that corridor up, and you have a waveguide. Silvery pipes that carry radar pulses to an airport antenna, or channel microwaves through a magnetron's copper maze. Inside, the waves ricochet, forbidden to leak because metal walls force electric fields to zero. It is as if the pipe whispers, "This way only." Sometimes, though, we want silence. Step into a Faraday cage, an elevator, perhaps, or a mesh room in a science museum. Your phone's bars topple, radio vanishes. Lightning outside cannot touch the notes of a delicate instrument within. The cage's metal skin herds currents that cancel incoming fields, much like noise-canceling headphones, but for space itself. You've practiced small-scale fieldcraft without noticing. Tilting a handset, raising it near glass, shifting to an open doorway. Your body, bags of salty water, soaks up microwaves, creating literal dead zones. A half-meter pivot can rescue the signal, letting waves slip past ribs and shoulder into the waiting antenna. Guiding, blocking, amplifying our species has learnt to fence with invisible lines. Turning an abstract lattice into highways, vaults, and whispers that crisscross daily life. Up to this point, waves appear tame. Brighten the bulb, grow the ripple, dim it, and energy wanes smoothly to nothing. But nature harbors a kink in that logic. One revealed with a simple slab of metal and a beam of violet light. Shine a dim gray lamp upon a zinc plate and nothing happens. Increase the brightness, and still the metal refuses to budge. Swap the lamp for a faint, ultraviolet glow, and ping. Electrons leap free like popcorn. No matter how weak the UV beam, each electron emerges with the same kick, as though light arrives not in sliding volumes, but in indivisible parcels. This is the photoelectric effect, and it shattered the classical picture. Light's field, it seems, is not infinitely divisible. It comes in quanta, photons whose energy depends on color alone. Brightness merely counts how many photons knock in quick succession, not how forceful each one is. The revelation opened floodgates. Lasers that weld steel yet carry music down optical fibers, solar panels that swap sunlight for charge, night vision goggles coaxing photons from a dim horizon. All exploit the fact that fields, when pressed to their smallest scale, reveal a grainy texture. So we arrive at a threshold. Classical waves guide compasses, songs, and Wi-Fi, but cannot explain why blue light frees electrons while red, however intense, does not. To continue, we must venture into a quantum landscape where every field wears two faces, smooth ripple, and countable spark. In the next part of our journey, we'll meet those sparks and see how particles emerge from the restless seas that truly compose the world. Picture a blacksmith's forge at dusk, iron rods glowing from cherry red to brilliant white. 19th century physicists tried to pin down that glow by pure mathematics and found, to their horror, a fatal glitch. The hotter the iron, the brighter the predicted ultraviolet light. So bright, in fact, their equations foretold infinite energy. Reality plainly disagreed. The universe does not explode in blue flame every time a stove warms soup. Enter Max Planck, a softly spoken German who approached the problem as one might negotiate a truce. If the forged metal could absorb or emit energy only in fixed coins, never in fractions, the runaway vanished. Planck did not know why nature would use such strict denominations. He called it a purely formal trick, yet the trick worked perfectly, and the size of each energy coin became h times frequency. A constant now etched on every physics wall chart. The message was revolutionary. Light, and by extension, every field may appear smooth. But when you zoom far enough, you find pixels. Increase the furnace's temperature, and you do not pour a continuous syrup of energy into space. You pay out more coins per second. Each coin's value is set by color. Deep red coins are modest, violet ones are lavish, ultraviolet coins pricier still. Takeaway: nature refuses small change below a certain denomination. Energy comes in indivisible packets, and that simple rule saves the world from mathematical meltdown. A few years later, Albert Einstein eyed Planck's energy coins and saw a bolder picture. If light exchanges energy only in set amounts, perhaps the light itself arrives as discrete clicks, tiny bursts he named photons. The proof lay in a humble slab of zinc. Shine a dim red lamp on the metal and nothing happens. Turn up the brightness, and still the surface sulks. Swap the lamp for a faint violet beam, far less total power, and electrons leap free at once. The metal is not impressed by sheer intensity, cares about each photon's color, its single coin value. Red coins are too small to buy an electron's escape, but violet coins pay the fee instantly. Brightness now gains a new meaning. Flood the plate with more violet photons per second, and you free more electrons. Yet each electron still exits with the same punch. It is as though you are tossing equal value tokens faster, not enlarging the tokens themselves. This photoelectric effect does more than illuminate solar panel ads. It confirms that the electromagnetic field, smooth and continuous to the naked eye, is actually a high-speed rain of quanta. Dial the wavelength shorter, and each drop lands harder. Dial it longer, and eventually the drops become too gentle to budge even a single electron. Takeaway: light is not a continuous glow, but a barrage of photons, individual energy coins whose worth is stamped by color, not brightness, and every modern solar cell, supermarket laser, and digital camera cashes in on that cosmic currency. Tap the edge of a crystal glass and listen to its ringing tone. That shimmer is not made by the glass sliding through the air like a flute. It is the lattice of atoms itself flexing. Billions of them moving together in regimented waves. Inside every solid atom sit like beads on springs. Jiggle one, and the disturbance spreads, not as a mushy shuffle, but as crisp packets of vibration called phonons. Think of a theater stage populated by dancers linked at the wrists. A single tug sets a ripple that passes from performer to performer, yet no one leaves the stage. In the quantum script, that ripple is indivisible. The entire troupe either shares one phonon or none. Crank the energy, and you don't stretch the wave taller. You invite more phonons to join the tour. Magnetic materials host a similar cast of characters. Flip one atomic compass, and a ripple of spin flips sweeps outward. The quanta of that wave are magnons, tiny magnetic murmurs that choreograph everything from credit card stripes to ultra-fast data storage. These quasi-particles matter because they explain the everyday. Heat in a metal rod is simply a bustling crowd of phonons. A click in a hard drive is a magnon ballet. They also hint at a deeper unity. Whether light in a vacuum or sound in a crystal, nature parcels energy in discrete packets. Fields differ, but their bookkeeping is the same. No partial coins allowed. Takeaway: even the solidity of a dining table vibrates in fixed quanta. Phonons and magnons reveal that matter itself plays a quantized melody beneath our fingertips. To grasp the next leap, imagine a placid pond at dawn. Flick the surface and concentric rings hurry away. That is a wave. But drop a steady rhythmic plunger, and you can set up a standing pattern. A persistent mound, a rhythmic bob that seems almost like an object perched on the water. In field language, a particle is just such a self-reinforcing ripple. Visualize the electron field filling all of space, as uniform and invisible as the air around you. Most of the time it dozes in perfect calm. But at a precise pulse of energy and a stable wobble appears a localized disturbance with fixed mass, charge, and spin. That wobble is an electron. Move the energy and the wobble melts back into quiet field. Electron gone without a trace. Creation and annihilation might sound dramatic, yet they happen everywhere. Strike a match. Thermal jostling spawns pairs of electrons and their antiparticles, positrons, for the briefest instant before they recombine into photons that warm your skin. Inside a PET scanner, positrons meet electrons, vanish. And their field energy re-emerges as back-to-back gamma photons the machine maps into medical images. In this view, vacuum is merely the field at rest, and matter the choreography of its excited steps. No billiard balls, no mini-planets, just ripples of differing styles. What feels like substance is a sustained vibration. What we call nothing is a stage ready to sing. Takeaway. Every particle from humble electron to elusive Higgs is a persisting wave in its own field. Proof that reality is woven not from things but from enduring patterns of motion. Switch on a humble LED torch and a quiet marvel begins. Inside the fingertip-sized chip, electrons sit on one shelf of energy. Holes wait on another. When an electron drops to join a hole, it must shed a precise coin of energy. So out pops a photon of equally precise color. Billions of these drops each second make a steady beam, yet each leap is all or none. Dim the torch and you simply invite fewer leaps. The photons themselves never shrink. Slide your phone across a payment terminal. The glass back whispers in near-infrared photons that bounce off a tiny mirror inside and return in time to confirm identity. Every pulse is a regimented column of identical quanta, drilled by a microscopic laser. That same discipline drives fiber optic cables, where coherent photons sprint through hair-thin threads, ferrying live concert streams beneath oceans. Walk into a hospital's cancer ward, and you may meet a device called a linear accelerator. It whips electrons to near-light speed, then slams them into a metal target. The violent stop spawns a flash of high-energy photons, breath-precise quanta tuned to disrupt tumor DNA while sparing neighboring cells. Even healing, it turns out, is a negotiation with energy coins. From grocery store barcode readers to the quantum random chips, securing online banking, modern life is awash with gadgets that juggle photons, phonons, and electrons in discrete handfuls. We rarely pause to notice, but every flicker of an indicator light is a field announcing. One packet delivered, next one on the way. Takeaway. Technology thrives on the field's small change. Devices work by counting, guiding, or swapping individual quanta, never by pouring a continuous stream. Electromagnetic ripples, electron waves, phonons in crystal lattice. We've met several fields, each with its own family of quanta, but these are not isolated performers. They weave together into an intricate tapestry scientists call the Standard Model. Picture a vast quilt where every colored patch is a field, stitched to its neighbors by threads of interaction. Some stitches glow, those are the forces, while others pinch tight, giving particles mass or dictating how they decay. Within this quilt flows an invisible sea, the Higgs field. Unlike the wavering patches we've explored, the Higgs rarely flutters. Instead, it sits at a steady non-zero level everywhere, like a gentle fog. As quark and electron ripples move through that fog, they feel resistance, the origin of what we casually weigh on bathroom scales. Gluon fields bind quarks into protons, neutrino fields flit almost unnoticed through entire planets, and photon fields keep your Wi-Fi alive. Each follows the same quantum grammar, energy coins, creation dances. Annihilation bows, but each speaks with its own accent, defined by charge, spin, and symmetry. In the chapters ahead, we'll tour this quilt in earnest. How symmetry keeps some ripples massless, why others confine themselves inside atomic hearts, and how a burst in 2012 revealed the Higgs patch by shaking the entire fabric at CERN. For now, hold this image. The solidity of the world is a busy marketplace of overlapping fields, each trading quanta under rules as strict as they are elegant. Takeaway: all known matter and forces fit into a single stitched panorama of quantum fields. Next, we'll unfold that panorama square by square. Spread a quilt across an oak table and run your fingers over its seams. Each patch is cut from different fabric, some coarse, some silky, yet the stitching holds the whole together. Modern physics describes the universe with a remarkably similar handiwork. Every square is a field. Quarks and electrons, photons and gluons, the elusive Higgs. The threads where squares meet are the interactions. The rules that let ripples in one patch tug or transform ripples in another. Most of the quilt's area belongs to matter fields. 6 quark patches and 6 lepton patches. Patterned in repeating families like motifs in grandma's folk art, draped over and through them are the force fields. Photons for light, gluons for the strong force, and the heavier W and Z for the weak interaction. Finally, Beneath the entire spread lies a subtle backing cloth, the Higgs field, so understated. You notice it only when you lift the quilt and feel its unexpected weight. Why arrange reality this way? Because patches lend stability. With each field confined to its own square, ripples keep their identity. Electrons never blur into photons, quarks stay stitched inside protons, yet the seams allow conversation, assuring the cosmos isn't a silent gallery of separate exhibits, but a humming bazaar of exchange. For the next few minutes, we'll tour this patchwork up close, square by glowing square. Beginning with the one you already greet each sunrise, the photon field that turns electricity into daylight. Takeaway: the universe is not a single cloth, but a quilt of interlocking fields. Its seams are the forces that let everything talk to everything else. Reach for a light switch, and with the tiniest click, a river of photons floods the room, bouncing off books, skin, and cat whiskers before vanishing into the walls. That effortless illumination springs from the quilt's brightest patch, the photon field, custodian of electric charge and all things electromagnetic. Imagine two tiny foam balls, each rubbed with wool until they bristle with static, then suspended on silk threads. Bring them close, and they drift apart, repelled by a force that seems to act through nothing at all. In field language, each ball shakes the photon patch ever so slightly, and the Quanta photons relay that shake to the neighbor, whispering, "Move away." The balls themselves never meet, the message carries the push. Scale the idea upward, and you have every power grid on Earth. Electrons marching through copper wires jostle the photon field. Distant electrons feel those nudges and shuffle in sympathy, lighting homes, driving trams, charging midnight phones. Replace wires with antennas in the same field: ferries, radio, radar, and Wi-Fi. Ripples launched by one coil of metal and caught by another, kilometers apart. Unlike the strong or weak force, the photon carries no mass. Freed from inertia, its quanta sprint at light speed and never tire. Which is why a galaxy 2 million light-years distant can paint its image on a backyard telescope. Yet the photon obeys one strict rule. It speaks only to charges. Neutrinos pass through walls because they carry none. Electrons laden with charge cannot ignore the field for a heartbeat. Takeaway: photons are the universe's postal service for charge, delivering pushes and signals alike at the fastest speed nature allows. Peer inside a proton, if imagination allows, and you won't find marbles neatly packed together. Instead, 3 quarks jitter in a storm of shimmering threads. Those threads are carried by gluons, the quanta of the strong force patch. They behave like no other stitches in the cosmic quilt. Unlike electric lines that fade with distance, gluon threads stretch like unbreakable rubber bands. Tug one quark outward, and the strand tightens, storing more and more energy. Pull harder still, and something astonishing happens. The band refuses to snap. Instead, it pinches off, the stored energy conjuring a brand new quark-to-quark pair that ties off the loose ends. The would-be escapee is recaptured. Free quarks remain as mythical as unicorns. This peculiar feature, it's called confinement, explains why atomic nuclei are rock solid, despite the electromagnetic repulsion of their positive charges. Within femtometers, gluon glue overpowers every other push or pull. You glimpse its legacy each time a kitchen smoke detector chirps. Inside, alpha particles born in nuclear decay barge through air, because their quark bundles stay perfectly sealed. Half a century ago, scientists at SLAC hurled electrons into protons and saw them ricochet off tiny hard spots, evidence that quarks exist, yet never fly free. The pattern resembled flashlight beams scattering from beads buried in jelly. The beads were there, but always wrapped in gelatinous gluon goop. Takeaway: gluons weave color-charged threads so tenacious that quarks live forever stitched together, making protons and neutrons the unbreakable bricks of matter. Turn a smoke detector over and you'll find a postage stamp speck of americium quietly emitting alpha particles. That decay, and the nuclear transmutations that fuel the sun, rely on a far subtler field. The weak force, ferried by 3 hefty quanta, W+, W-, and Z0 bosons. In the quilt metaphor, these messengers are padded squares, thick with mass, thanks to their constant slog through the Higgs fog. Because moving something heavy requires effort, their influence reaches only across an atomic nucleus before sputtering out. Yet within that tiny reach they wield transformative power. They can flip a neutron into a proton, or an electron into a ghost-like neutrino, rewriting the very identity of particles. When two protons in the sun tunnel close enough to embrace, the weak force whispers to one, "Shed your positive cloak, become a neutron." A W+ boson appears for a fleeting instant to carry charge away, birthing a positron and a neutrino. Without that rare permission slip, stars would never ignite. Starlight is, at heart, a weak force signature. Catching these messengers required audacity. In 1983, inside CERN's gargantuan bubble chambers, physicists blasted protons and antiprotons together at record energies. Among the swirling tracks, they glimpsed thick, stubby spirals, the footprints of W and Z bosons decaying in fractions of a trillionth of a second. The discovery confirmed the electroweak theory and completed another patch of the standard model quilt. Takeaway: though short-ranged and ponderous, the W and Z bosons govern the alchemy of the nucleus, lighting stars and powering detectors with transformations no other force can perform. Walk through a morning mist and you feel almost nothing, yet droplets cling to coat and hair, adding a gram here, a gram there. The Higgs field is much the same, only it never burns off under sunlight. It permeates every cubic centimeter of the cosmos, entirely invisible, yet quietly influential. When certain ripples, electrons, quarks, W and Z bosons move through this fog, they experience resistance. That resistance is their mass, not extra stuff glued on, but reluctance to accelerate the way swimmers feel drag even in still water. Why then, do photons glide mass-free, while W lumber under 90 proton masses? Because the Higgs fog is picky. It couples fiercely to some fields, gently to others, and ignores the photon altogether. It's much like thick carpet slowing a boot, but letting a flying insect pass untouched. The measured strengths of those couplings read like a fingerprint of reality. Top quarks, heavy and foot-dragging. Electrons light as dust. Neutrinos, all but oblivious. Proving the fog exists required shaking it hard enough to make it ripple on its own. In 2012, proton collisions at CERN briefly agitated the field into an excited state. The Higgs boson, it lived for a whisper of time, then fell apart into photons and other debris, leaving a distinctive bump in the data, tiny splash announcing the presence of a limitless sea. Takeaway: mass is not an intrinsic brick, but the drag of a universal mist. Discovering the Higgs boson was our first direct splash in that omnipresent fog. Imagine a kitchen recipe so forgiving you can add equal pinches of salt and pepper without changing the flavor. That freedom, swap a little of one for the other, taste stays the same as what physicists call asymmetry. In the standard model quilt, each patch begins with similar freedoms. Tweak a quantum phase here, rotate a charge there, and the underlying laws hum along untroubled. But symmetries, like recipes, can shift when conditions cool. Water vapor is perfectly uniform. Lower the temperature and ice crystals pick specific angles, sacrificing symmetry to gain structure. The universe followed a similar path. At searing early cosmic temperatures, the electromagnetic and weak patches were one blended broth, the electroweak field. As the cosmos expanded and cooled, the Higgs fog condensed, forcing the broth to separate into two distinct flavors: a long-range photon field and the short-range heavy W and Z fields. A beautiful freedom broke, and from that fracture emerged the diverse forces we observe today. Symmetry breaking echoes in familiar places. Liquid helium slides into a superfluid that flows without friction only after losing rotational symmetry. Each case reveals the same lesson. When a system lowers its energy by picking one option among many, it leaves telltale patterns. What scientists hunt in particle colliders and condensed matter labs alike, Next, we'll explore how such broken threads tie into everyday technology and point toward mysteries the quilt has yet to hem. It's from dark matter's unseen patches to gravity's missing square. Takeaway: the forces and masses we know are born when perfect symmetries tear. The universe choosing specific patterns and leaving imprints we can still trace today. Stand back from the quilt. We have toured and admire its vivid order. Photons stitching electricity to light, gluons knitting quarks into nuclei. W and Z bosons busy with elemental alchemy, the Higgs fog lending every ripple its heft. The pattern feels satisfying, almost finished. Yet along the borders, the fabric frays into darkness, threads trailing into questions no loom has yet answered. Peer into the night sky, and you'll see galaxies spinning too fast for the visible stitches to hold. Something unseen, dark matter, tugs at every star, yet no patch on our current quilt matches its pull. Measure the universe's growth, and it accelerates. As though the very quilt were stretching from some hidden elastic, we've labeled dark energy. It's gravity itself, so familiar you can feel it in your shoes, resists quantum stitching altogether. Hovering like a neighboring tapestry woven on different principles, even inside the quilt, tiny puzzles persist. Neutrinos jiggle between flavors, hinting at masses far lighter than the Higgs recipe predicts. The muon's magnetic wobble drifts from theoretical expectation, a possible whisper of an extra, undiscovered square. And at facilities worldwide, detectors sit beneath mountains or drift in space, waiting for any hint of new ripples that could extend our textile. So, map in hand, we find ourselves at the quilt's edge, a frontier where certainty ends and possibility billows outward like unsewn cloth. In the next parts of our journey, we'll step beyond this stitched comfort, from the restless vacuum where fields never quite rest, into laboratory universes built of superconductors and graphene, and finally, toward the daring notion that space-time itself might be yet another field awaiting its patch in the cosmic coverlet. Your takeaway: the standard model quilt is wondrous but unfinished. Its frayed borders beckon us to weave new threads, dark matter, dark energy, quantum gravity, into the ever-growing fabric of reality. Picture the quietest place on Earth, a steel chamber pumped emptier than interstellar space. Walls chilled until the final wisps of gas freeze solid. Turn off every laser, every lamp, every heater. By common sense, the stage should now be blank. No atoms, no light, perfect stillness. Yet when physicists lower a hair-fine microphone, a nanomechanical reed, they hear a faint murmur. The reed trembles, as though prodded by invisible fingertips. This is zero-point energy, the irreducible jitter of quantum fields. Even when we evict all matter and drain all heat, the fields themselves refuse to sit perfectly still. Like children instructed to be quiet at bedtime, they fidget in the dark, wiggling just enough to betray their presence. The electromagnetic field sprouts pairs of virtual photons that appear and vanish quicker than any camera can blink. Electron fields do the same with particle-antiparticle twins. Each flicker is tiny, but across the vast expanse of space, the aggregate hum becomes profound. Why can't the fields simply relax? Because quantum rules forbid absolute precision. Pin them to zero motion, and their energy becomes hopelessly uncertain. Nature chooses the gentler compromise, perpetual, minimal restlessness. It is quiet enough that our bodies feel nothing, yet insistent enough to tilt the weight of an electron, curve the orbit of hydrogen's lone passenger, and most wondrous shape the destiny of black holes. The stage, it seems, is never empty. It is a restless sea whose surface we mistake for calm night air. In a laboratory lit by the soft glow of oscilloscopes, two mere smooth metal plates stand face to face, separated by less than a human hair. They carry no charge, feel no classical pull, yet over days they creep toward each other with a measurable force strong enough at tiny gaps to snap fragile supports. No hand pushes them, no magnet lures them. The culprit is the restless vacuum itself. Between the plates, only certain electromagnetic ripples can fit, waves whose peaks align neatly with the narrow cavity. Outside, the full orchestra of wavelengths plays without restriction. The mismatch creates a subtle pressure difference. More modes jostle outside than in, so the plates are gently pressed together. This phenomenon, predicted by Dutch physicist Hendrik Casimir in 1948, is today verified with exquisite micro-machined levers. Engineers even harness it, sometimes grudgingly, in nanoscale gears where the Casimir glue can cause parts to stick, or, with clever design, to latch by intent. Visualize children jumping on a trampoline. If two hefty youngsters claim the center, fewer places remain for the others to bounce, so the surrounding crowd presses inward. The plates are those children. The vacuums, ceaseless modes, are the eager jumpers. Remove the plates, and the pressure equalizes. No squeeze. Insert them, and the imbalance reappears, a whispering force born from nothing at all. What feels like a magician's trick is merely quantum bookkeeping. Limit the room for fluctuations, and they push back. Even emptiness has preferences, and metals polished to atomic smoothness. Let us feel that phantom hand. Aim a glass prism towards sunlight, and Newton's tidy rainbow appears. Red, orange, yellow, through violet. Each strip marking a precise energy of light. But when physicists inspected hydrogen's spectrum with wartime radar gear in 1947, one crimson line sat ever so slightly out of place, nudged just a hair from theory. The culprit was not faulty glass. It was the vacuum again, slipping its invisible fingers into the atom. Inside hydrogen, an electron orbits a proton like a lone moon. Classical quantum theory said two particular orbits should share identical energy. Yet Willis Lamb's radio frequency measurements showed a minuscule gap. The Lamb shift. The restless zero-point photons swarm around the proton, momentarily polarizing space, and that tiny storm tugs on the electron's path. A trillionth of a second jitter lifts one orbit higher than the other. By a few parts in a billion, enough for careful ears to hear. Fast forward to today's muon G2 experiment. Muons, heavier cousins of the electron, loop in a magnetic ring. If empty space were truly empty, their magnetic wobble would match in-clean calculations. Instead, vacuum pairs spring into existence, cling to each muon for fleeting instants, and alter its precession. The latest data hint at a wobble beyond standard model expectations. Perhaps the vacuum hosts ripples from fields we have yet to sew into our cosmic quilt. Takeaway: even delicate spectral lines and subatomic compass needles reveal the vacuum's influence. Silent fluctuations leave audible fingerprints on the tiniest scales. Imagine floating in deep space, heater off, stars distant pinpricks. To you, the vacuum feels frigid and empty. Now fire up a rocket pack and accelerate hard. Strangely, a faint warmth seems to bathe your visor, according to physicist Bill Unruh. An accelerating observer perceives the vacuum as a thermal sea. Motion stirs virtual photons into reality, much as whisking cream conjures peaks from liquid smoothness. The faster you accelerate, the hotter the perceived glow, though reaching room temperature would demand unimaginable thrust. Stretch this idea to a cosmic extreme. The edge of a black hole. From afar, the event horizon looks like an inescapable one-way gate. Yet Stephen Hawking realized that quantum fields do not respect such absolutes. One member of a virtual particle pair can fall inward, leaving its twin free to escape as real radiation. To distant eyes, the horizon itself glows. Hawking radiation. Ever so faintly, over stupendous timescales. That glow will bleed a black hole dry and returning its locked-away mass to the wider universe as whispers of light. Both effects share a moral. What counts as nothing depends on how you move. Inertia sees calm, acceleration sees heat. Gravity, by bending space-time, can mimic endless acceleration, turning the silence around a black hole into a subtle hiss. Our concept of vacuum is therefore not universal, but perspectival. A reminder that reality is richer than any single vantage point can reveal. Your takeaway: change your motion, or stand near a horizon, and the vacuum itself lights up, proving that emptiness is in the eye and speed of the beholder. Listen closely to a quiet audio recording and you'll notice hiss, the unavoidable static of microphones and electronics. Light carries its own hiss, a jitter born of zero-point energy. For decades, that quantum rustle set the sensitivity floor of the world's finest instruments, till physicists learned to squeeze it. Think of uncertainty as a partly filled water balloon. Press it narrower one way, and it bulges elsewhere. In quantum optics, we do the same with the vacuum's noise. Special crystals, bathed in laser light, reshape the random fluctuations, so that one property of the light, the phase, say, grows calmer, while its partner, the brightness, gets extra jitter. Choose which side matters for your measurement, and the unwanted rumble drops away. The payoff is grand. LIGO, the observatory that hears black holes collide, injects squeezed light into its kilometers-long cavities. The calm phase lets laser beams register mirror motions smaller than a proton's width, turning what was once vacuum static into a sharpened ear for space-time tremors. In superconducting circuits, engineers coax vacuum fluctuations to split into real photon pairs, our microwave echo of the Casimir Effect, feeding quantum computers with tailor-made signals. Future clocks may beat with accuracy limited only by how well we can sculpt vacuum noise. Dark energy detectors now on drawing boards plan to use squeezed states to sniff the universe's faintest pushes. What earlier generations called empty has become pliable raw material, a medium we mold like glass into lenses for the very small and the very distant. Your takeaway? By squeezing the vacuum's built-in jitter, we transform quantum rustle into a precision tool, proving that even silence can be engineered. We began this chapter seeking emptiness and found instead a restless stage, plates that feel ghostly pressure, atoms nudged by unseen hands, horizons that glow if you rush toward them, and clever machines that sculpt the hush into sharper hearing. The vacuum is not a backdrop but a character, forever whispering beneath the louder actors of matter and light. Yet physics offers another revelation. We can create new vacua, tailor-made ground states inside everyday materials. Cool aluminum to a few degrees above absolute zero, and its electrons pair off, birthing a superconductor where electric ripples flow without resistance. Carve carbon into honeycomb sheets and graphene hosts Dirac-like quasi-particles that sprint as if massless. Twist to such sheets to a magic angle and an entirely different set of rules emerges. Complete with its own Higgs-like gaps and superconducting phases, these condensed matter landscapes act as miniature universes, each with distinctive fields, particles, and symmetries. Laboratory playgrounds where we can tune the laws at will. They promise technologies from lossless power grids to topological quantum bits. But more importantly, they let us probe questions too extreme or too expensive to test in particle colliders or deep space missions. In the next part of our journey, we will step into these man-made worlds. We'll watch electrons glide friction-free, meet quasi-particles, stranger than any standard model citizen, and learn how emerging fields and solids mirror, and sometimes mock, the grand fields of the cosmos. Your takeaway. If the true vacuum is a restless sea, condensed matter physics invites us to bottle new seas. Pocket universes where the rules of reality can be rewritten and explored. Lower a simple ring of lead into liquid helium, and a hush descends inside the metal. Electrons that once jostled like commuters at rush hour now pair off 2 by 2 into Cooper pairs. The pairs are not separate passengers, they merge into one grand quantum state, a single wave that fills every corner of the lattice. In that collective whisper, electrical resistance vanishes. Push a current and it loops forever, slowed by nothing, as though the copper atoms had turned to glass. Set a small magnet above the chilled ring, and another wonder appears. Lines of magnetic flux, usually free to thread metal, are expelled outright. The Meissner effect. The magnet hovers, locked in an invisible cushion made by the superconductor's refusal to admit the field. What looks like levitation is simply the new vacuum of the Cooper pair C, asserting its boundary. No magnetic trespassers allowed. Hospitals harness this hush every day. MRI scanners use superconducting coils to summon steady fields so strong they can coax the spins of hydrogen nuclei into radio-visible choreography, hence revealing tumors, ligaments, the flutter of unborn hearts. Engineers dream further. Citywide power lines, without a watt of loss. magnetically levitating trains whispering at 600 kilometers per hour. Quantum computers whose fragile bits are shielded by the very silence that banishes resistance. Your takeaway: chill certain metals and their electrons link arms, creating a new vacuum where electricity flows without friction and magnets ride on cushions of excluded field. Proof that changing the ground state can rewrite nature's rulebook. Crack a pencil trace under a microscope and peel away a single sheet. You hold graphene, carbon pared down to 1 atom thickness. Arrange those atoms in a honeycomb, and the electron field inside reshapes its rules. Charge carriers now behave like massless Dirac fermions, racing across the sheet at 1/3 of light speed, immune to many impurities that would trip ordinary electrons. It is as if a fragment of deep space physics has slipped onto a laboratory slide, because these quasi-particles carry almost no inertia. They barrel through corners without backscattering, letting currents glide with unexpected grace. Apply a magnetic field and their energy levels snap into clean steps. The half-integer quantum Hall effect, confirming that the sheet hosts its own brand of relativistic playground. Engineers are quick to listen. Transparent conductors thinner than a soap bubble promise bendable phone screens. Ultra-fast transistors switch trillions of times per second without heating like silicon. Researchers have even shaped graphene into nanodrums that vibrate with such precision. They can weigh a single virus. Yet the true marvel is conceptual. By rearranging familiar carbon, we summon a vacuum where electrons forget their mass. Classical matter becomes a testbed for high-energy ideas, no particle collider required. The sheet in your tweezers is both material and metaphor, tangible evidence that the laws we learn in cosmic accelerators can emerge by clever geometry alone on the tip of a pencil. Your takeaway: graphene turns everyday carbon into a landscape where electrons sprint like massless light, showing that new geometries can conjure new physical laws right in the palm of your hand. Take 2 flawless sheets of graphene, stack them, and nudge one ever so slightly 1.1 degrees off perfect alignment. This minor twist, thinner than a dragonfly's eyelash, transforms the electronic score beneath. The one-speeding Dirac fermions slow to a crawl. Their energy bands flatten like piano keys laid end to end. In the stillness, interactions that were background chatter grow thunderous. And the material shifts personality at a whisper of gate voltage. First, an insulator that blocks all current, then flick. A superconductor that carries it without loss. Scientists call the craft Twistronics, using geometry as a tuning dial for nature's constants. Just the angle by a fraction of a degree, and you watch a tabletop universe switch genres. From Mott insulator blues to superconducting jazz, the laboratory control is dazzling. Electric fields slide the 2 sheets back and forth in situ, letting researchers paint phase diagrams as artists mix color. Why does the twist matter? The misalignment creates a Moira lattice, kilometers wide on the electron scale, corralling them into standing waves that magnify their mutual push and pull. It is as though a stadium wave slows a sprinting crowd, giving neighbors time to lock arms and attempt new choreography. Practical horizons: sparkle superconductors that work closer to room temperature. Ultra-sensitive strain sensors, quantum bits born of correlated states. But the deeper wonder is philosophical. A gentle rotation of carbon layers rewrites physical law, reminding us that geometry itself can be an author of reality. Your takeaway: a 1-degree twist between graphene sheets births an entirely new rulebook. Proof that the angle of a lattice can orchestrate phases of matter unheard of in untwisted space. Picture a 2-dimensional plane of electrons cooled to a hush and swept by a powerful magnetic field. In the interior, motion freezes, like cars marooned in a desert storm. Yet along the perimeter, traffic surges. Electrons zip one way round the border in perfectly disciplined lanes, immune to potholes or roadblocks. This is the quantum Hall effect, a topological marvel where the bulk of the material becomes an insulator, but its edges host friction-free highways. Topology cares not for microscopic bumps, prizes whole shapes such as loops, twists, cuts that cannot be undone without tearing the fabric. In a quantum Hall fluid, the electron sea takes on a global twist. And that twist guarantees the edge current much as the rim of a vinyl record guarantees a closed groove. You can dent the surface, sprinkle impurities, even remove atoms. The current skirts every obstacle unruffled. Delve deeper, and the passengers themselves grow strange. In certain fractional quantum Hall states, collective ripples break the electron into anyon. Quasi-particles carrying fractions of a charge and dancing to statistics, neither fermionic nor bosonic, braid two anyons around each other, and the system remembers the path. Not just the meeting, an intrinsic memory that engineers hope to sculpt into fault-tolerant quantum bits. One can already watch these edge states light up as microwaves trace their loops, or measure an ionic charge in delicate tunneling experiments. Each observation hints that information can ride on topology's robustness, promising electronics that shrugged off disorder as mountains shrugged off raindrops. Your takeaway. In topological materials, the interior may slumber, but edges come alive with indestructible currents and exotic anyons. Highways and travelers shaped by geometry rather than chemistry. In a basement lab, awash with ruby-red laser beams, physicists chill a puff of rubidium gas until the atoms move slower than a drifting snowflake. Crisscross the lasers, and they form a standing wave egg crate of light, an optical lattice. Each trough traps a handful of atoms. Dial the laser intensity, and you can make the wells deep or shallow, close or far apart. With knobs and sliders, scientists recreate on a tabletop the intricate Hubbard model that once lived only in chalkboard dreams. Need stronger interactions? Sweep a magnetic field and a Feshbach resonance lets atoms link hands more tightly? Want a charged particle in a magnetic field? Shake the lattice rhythmically, and a neutral atom feels a synthetic Lorentz force, tracing tight cyclotron orbits without a single electron in sight. Within this light-built city, researchers watch superfluids freeze into Mott insulators, measure sound waves racing at record low temperatures, even glimpse analog Hawking radiation as density ripples escape an artificial horizon. Photons themselves can be herded too. Drill microscopic holes in silicon, and you craft a photonic crystal, a landscape where certain colors roam while others are banished. Curve the crystal's pattern, and light behaves as though space has bent. Vary the index, and you give photons a synthetic mass. Recently, waveguides etched in glass coaxed entangled photons to mimic relativistic particles tunneling through potential barriers. Quantum field theory enacted at the speed of light. Here we are no longer mere observers of nature's laws, or composers, scoring new symphonies of forces and particles with laser light, magnetic wands, and lithographic chisels. Your takeaway. Cold atom traps and photonic lattice let scientists build pocket universes. Programmable arenas where forces, masses, and even horizons are dial-a-law creations. Across this chapter, we have seen matter made to levitate, electrons stripped of mass, and edges that host immortal currents. We have twisted carbon into superconductors, braided anyons for memory, and used laser light to summon synthetic gravity inside a glass chip. Each experiment whispers the same radical suggestion: physical law is negotiable. Change the vacuum, the geometry, or the interaction pattern, and new fundamentals unfold. That insight now nudges us toward an audacious frontier. If a 1-degree twist can conjure fresh particles, if a standing wave can mimic an event horizon, might spacetime itself be an emergent fabric, woven from deeper quantum threads we have yet to glimpse? Theoretical physicists propose that entanglement could knit distance, that wormholes might be entangled pairs writ large. Gravity could arise the way elasticity emerges in a crystal. Collective, inevitable, but not primary. In the episodes ahead, we will step onto that frontier. We will explore how quantum information may be the loom of geometry, how networks of qubits simulate black hole interiors, and why the dark energy stretching galaxies apart could be a clue that our cosmic quilt is still on the needles. So keep the image of the laboratory universe in mind, a cold atom cloud glowing orange in laser light. In that tiny human-made cosmos, we catch a preview of a deeper truth. Reality is not a rigid monument, but an ongoing weave, and we, the curious, have begun to tug at the threads. Your takeaway? The ease with which labs rewrite microscopic law hints that even space-time may be a fabric still being woven. Our next journey shall follow those emerging strands. Imagine floating far above the Milky Way, watching its spiral arms sweep like slow fireworks. Zoom in past nebulae, planets, cells, atoms, till the familiar dissolves into abstraction at about 10 to the power minus 35 meters. 20 orders of magnitude beneath a proton, every theoretical roadmap falters. This is the Planck length, often portrayed as nature's final decimal place. A scale so small that distance itself may fragment into quantum pixels. Why suspect such granularity? Because to measure position ever more precisely, you must probe with ever shorter wavelengths, higher energies that eventually would fold space upon itself, forging tiny black holes. Beyond that brink, the very concept of where blurs. Space-time foams like boiling water, frothing with momentary tunnels and twists. Two mirrors placed closer than a Planck length could not reflect light in synchrony. Uncertainty would shove them apart. In this view, Einstein's smooth fabric is a zoomed-out illusion. It's like a photograph that conceals its dot pattern until you press your nose to the glass. Physicists liken the Planck scale to the weave of a carpet. From across the room, the carpet seems continuous. Under a magnifying glass, knots and fibers appear. We have not yet built an instrument sharp enough to glimpse those knots, but cosmic clues hint they are there. The maximum information a black hole horizon can hold, the tiniest jitter in gravitational wave phases, is the fact that nothing outruns light. All whisper that space-time may be less a stage and more a tapestry whose threads we are only beginning to discern. Your takeaway. Beneath the calm curves of relativity, space-time may resolve into Planck-scale pixels, tiny knots that set the ultimate limit on here and there. Picture a vast social network. Friends, families, colleagues, linked by invisible ties of familiarity. Two strangers separated by oceans can feel close if mutual friends knit a short path between them. Now replace people with quantum particles, friendships with entanglement. And you have a provocative idea. Distance might be nothing more than the pattern of who is linked to whom. In 2013, theorists Leonard Susskind and Juan Maldacena proposed a cryptic equation. ER equals EPR. On the left, Einstein-Rosen ER bridges, wormholes that bend spacetime into tunnels. On the right, Einstein-Podolsky-Rosen EPR pairs. Entangled particles, sharing a unified quantum state, conjecture suggests these two notions are different faces of one underlying fabric. Stitch two particles with entanglement, and a microscopic wormhole lurks between them. Non-traversable, but real enough to define connectivity. Under this lens, space-time is not laid out like graph paper. It is woven from correlations. High entanglement density means threads pulled tight, regions feel nearby. While sparse entanglement lets the fabric sag, regions drift apart. Black hole horizon, saturated with entanglement, becomes a densely stitched curtain. Sever enough threads, and the curtain frays, echoing the black hole information paradox. Laboratory hints already glimmer. In certain quantum simulators, engineers dial entanglement patterns and watch effective geometry curve or flatten in response. It's as if friendship links on a social graph were rearranged, causing entire neighborhoods to drift nearer or farther without moving a house. Your takeaway. Entanglement may be the loom on which distance itself is woven. An unseen network whose connectivity decides what counts as far and what counts as near. Hold a credit card to the light, and the tiny hologram shimmers. A three-dimensional image conjured from a two-dimensional foil. Black holes, those dark sentinels of the cosmos, hint that reality may employ a similar trick on the grandest stage. When Jacob Bekenstein and Stephen Hawking studied black hole thermodynamics, they discovered a startling rule. The entropy, meaning the information content of a black hole, scales not with its volume, but with the area of its event horizon. Pack twice as much matter inside, and the informational budget grows only with the surface. As though every new byte must fit on a horizon-wide memory card. Extend that principle beyond black holes, and you arrive at the holographic hypothesis. Perhaps our entire universe is like the credit card foil. Its three-dimensional happenings encoded on a distant two-dimensional boundary. In some mathematical arenas, space-times with a negative curvature called adds. This notion becomes precise. Gravity in the bulk equals a quantum field theory on the border. A cosmic translation dictionary known as a DSCFT, duality. Even our accelerating universe, more de Sitter-like than adds, may whisper holographic hints. Cosmic microwave background data show information stamped on a spherical horizon 46 billion light-years away, our observable edge. If the hologram idea extends here, then the drama of galaxies, life and thought could be a richly rendered interior generated by pixels on that remote screen. Your takeaway? Black hole physics suggests the universe may be a hologram. Its deep volumes encoded on faraway surfaces, turning space itself into a grand projection. When engineers guard your cloud photos, they scatter each file across multiple servers. Lose one hard drive, and the picture survives. Error correction by redundancy. Astonishingly, cutting-edge theory proposes that space-time knits itself together by the very same strategy. In tensor network models like Mera, physicists represent quantum entanglement as a layered web of nodes and links. Feed in a pattern of intertwined qubits in a curved geometry. Complete with gravitational behavior emerges from the mathematics. Here's the key. Remove or scramble a few qubits deep inside the web, and the larger pattern endures. The network's entanglement redistributes the missing information. Healing small wounds, much like a geodesic dome, transfers stress. That robustness mirrors spacetime's resilience. Poke a tiny hole in the vacuum with particle experiments, and the fabric flexes, but does not tear. Gravity's smoothness may be the macroscopic face of an error-correcting code humming beneath. Laboratory analogs already sketch the idea. In superconducting circuits, researchers entangle microwave photons into surface codes that self-repair against local noise. The logical qubit lives not in any single photon, but in the global weave. An echo of how a chunk of space might reside in correlations rather than points. Scaling such systems could let physicists build toy universes, watching geometry morph as they tweak the code. If correct, gravity's gentle insistence on keeping the cosmos continuous is neither magic nor coincidence, is information theory writ large. Redundancy ensuring the stage stays intact, so the cosmic play can proceed. Your takeaway: spacetime's smooth fabric may arise from quantum error correction, with entanglement redundancy acting as the unseen mason that keeps the universe whole. For decades, quantum gravity lived only on chalkboards, symbols nested within symbols, forever beyond the reach of instrumentation. But the experimental tide is turning. Engineers are fashioning stethoscopes, sensitive enough to eavesdrop on the Planck scale whisper. Begin with gravitational wave echoes. When two black holes collide, LIGO records a dying chirp. Some theories predict faint, later reflections, ripples bouncing off quantum corrections near the horizon. Analysts now comb petabytes of data, stacking events to amplify any echoes a billion times fainter than the main shout. A positive signal would be our first acoustic portrait of spacetime's microscopic grain. Closer to Earth, diamond anvils and optical traps cradle nanoparticles, 1,000th the width of a hair. Researchers cool these beads into quantum superposition, two locations at once, separated by mere nanometers. Let Earth's gravity act on both arms of the superposition. And any deviations from Newton's script could hint at quantum gravitational influences. Surfacing not in distant quasars, but on a bench dot. Even radio astronomers have joined the hunt. Pulsar, timing arrays. Galactic metronomes spread over the Milky Way. Listen for dewdrop-sized fluctuations in signal arrival times. A jitter unaccounted for by cosmic dust or dark matter might betray spacetime foam. Each Planck scale jitter, adding its microsecond signature to the centuries-long beat. Pull off these feats, scientists borrow tricks we met earlier. Squeezed light, superconducting qubits, cold atom interferometers. The same field mastery that weighs viruses and maps brain tissue is now repurposed to weigh the very fabric of the cosmos. Your takeaway: quantum gravity moved from blackboard conjecture to lab challenge. The first delicate instruments now press an ear to space-time's deepest murmur. We have wandered from Newton's apple to vibrating graphene, from laboratory horizons to cosmic holograms. Along the way, a pattern emerged. Reality is woven, not built. Fields ripple, entanglement knots, error-correcting codes, patch holes, and even emptiness hums with possibility. Each layer we peeled back revealed another loom beneath, spinning finer threads. Yet questions dangle like loose yarn at the border. What ties quantum information to the arc of gravity with absolute rigor? How do dark matter and dark energy stitch themselves into a picture seemingly tailored without them? Can entanglement alone explain the arrow of time, the spark of consciousness, the birth of the first star? Our series will close by confronting these open seams. Episode 10, Reality is Relationships, gathers every strand. Gravity's shape, quantum's dice, symmetry's code, inertia's stage, the restless vacuum. Lab-made universes, and space-time's emergent weave, into one tapestry of connectedness. The finale will ask not merely what the universe is, but why its fabric allows meaning, memory, and marvel. For now, stand beneath the night sky once more. Recognize that the distance between you and Andromeda, the rhythm of your heartbeat, and the glow of your phone screen are all expressions of a single, ongoing act of weaving. We are threads within the loom, conscious knots briefly aware of the pattern unfolding around us, and perhaps with curiosity a shuttle, capable of adding a stitch or two of our own. Your last takeaway for tonight? At the loom's edge, we glimpse unfinished cloth. Questions still unraveled, setting the stage for our final meditation on a cosmos made of pure relationships. Stand outside on a wind-stilled evening. The sky hangs like dark velvet, punctured by points older than Earth itself. To the naked eye, it feels complete, its unchanging constellations, planets tracing familiar loops, a moon that has risen and set for every ancestor you have ever had. But listen a moment longer, past the crickets, past your own pulse, and imagine the hush alive with inaudible weaving. First come the fields, unseen oceans, whose gentle ripples become electrons, photons, quarks. They are the loom's first threads, caught across all of space and time, yet the weave does not end there. Entanglement knots those threads into patterns that define nearness and distance. Carving valleys we call gravity, stretching sheets we label spacetime. Even the vacuum, which we once dismissed as nothingness, is thick with jitter, an ever-busy shuttle adding texture to the cloth. Human hands have begun to imitate the craft. We coax electrons into frictionless rivers, twist carbon until massless quasi-particles race across a tabletop, trap atoms in lattice of light that echo the mathematics of black hole horizons. Each experiment is a pocket universe, proof that the rules we revere can bend, fracture, or bloom into entirely new sets when the underlying weave is retuned. And still the loom hums beyond our reach. Planck-scale knots may pixelate reality more finely than any microscope will ever resolve. Dark matter prowls between the stitches. Dark energy tugs the fabric outward faster each epoch, as though an unseen hand were tightening a cosmic frame. We have traced the pattern far, yet the edges fray into questions more profound than any answer we have yet secured. What does it mean to live inside a tapestry forever in the making? It means solidity is an illusion of scale. Every stone, thought, and heartbeat is a momentary standing wave in a deeper sea. It means discovery is not a conquest, but a conversation with the loom itself, its measurement a polite request. Each paradox an invitation to look closer. So the next time you tap your phone, ride a levitating train, or gaze at the Milky Way swirling over a quiet lake, remember, you are engaging with fabrics both ancient and newborn. The charge that powers your screen, the superconducting hush beneath a hospital magnet, and the spiral arms arcing through space all arise from the same silent workmanship. This is cosmic canvas, where the universe is not only studied, but painted in meaning. Until next time, keep asking, keep looking up, and never stop wondering.